It might be a sort of an odd question to ask of a company which is fundamentally based around science and technology, but why do we have an R&D department? What are we aiming to achieve? What are we trying to do? So there's really two sort of twin pillars that underpin our R&D. And the first of those is around the quality and the quality of the product, the quality of the service we deliver, and our resilience in the marketplace. And Rob touched a little bit in his address that I think really the last couple of years has seen PhotonAssay transition from a new technology that has to compare against fire assay to being seen as a technology which really is a market leader, particularly for challenging or difficult to measure deposits. And from that position as market leader, we need to make sure not just that we're delivering a good service, but that we're delivering the best possible, the most precise, the most accurate service that we can for gold. Quality is more than just the quality of the service that we deliver, though. It's also the quality of the products. And there's several factors that kind of come into that. So one area that we've really started to address in the last few years, and I'll talk at some length about, is supply chain resilience. So this is looking at where we both get our complete systems from, but also core components of that technology. We live in a world of, I guess we could say, increased geopolitical complexity, assumptions about availability of components, availability of materials that have always been historically true might not continue to be true. So thinking about how we as a company position ourselves to manage that is really important. Performance of our equipment means, again, beyond just are we delivering accurate results, is the equipment available when it needs to be? If we're supporting 24/7 mining operations that have come to critically rely on the fact that we're giving them real-time data, we need to be available to provide that data. We need to be able to keep the equipment operating easily around the world. As we've seen on the sort of the world map, we're in many different jurisdictions, many of them very remote. So availability of well-trained staff, spare parts are critical. How can we design or improve the designs of our equipment to make those things easier to support? And at the end of the day, how can we make our equipment easy to use? I mean, under the bonnet, PhotonAssay is a really complicated bit of gear. There's an awful lot of science and engineering that goes into it. But we very much tried to position ourselves as a technology that a user can set up, install, and operate in a relatively straightforward way. Then the other half of what we're doing is thinking about how can we broaden the offering. So we started off as a gold assay company. We've added silver and copper over the last few years. We're now really getting into where do we go to next? So how can we take PhotonAssay and expand it or extend it to do new elements, or to do elements in materials that historically we've not been able to look at or assay? What new technologies are there out there, either things that we can develop in-house or things that we can partner with science or engineering companies to bring into the mix of PhotonAssay? That might be measuring more commodities, more elements. It might be measuring new properties like mineralogy or density. And we're not just trying to get, I guess, broadly into any technologies. We're thinking about things that build on what we see as our core strengths, which is fast analysis on relatively unprepared materials. And then the last area that I'll talk a little bit about today is moving up and downstream. So if we view PhotonAssay as the analysis part of the business, upstream for us means thinking about where do our samples come from, how are they prepared, how do they get into the jars that go into the machine, and downstream means thinking more about data. So going beyond just reporting grade, how can we give people meaningful insights that help them run their mining or mineral processing operations more effectively? And within that sort of remit of broadening the offering, we've always got three factors that we consider: scale, need, and ability. So scale simply means, is there a big enough market opportunity that's worth investing R&D dollars into? Need means that really the existing technologies or the existing approaches on market have some deficit. Maybe they're expensive or polluting or slow or energy intensive. If there's a great solution out there, there's no point us trying to reinvent the wheel. We want to tackle problems where there isn't a good existing solution. And ability just means that what we're trying to do has to align with our strengths, the skills of the people we have, or paralleling or aligning with the sort of technologies that we build. So I'll start with just some thoughts about what does it mean to expand our footprint. So the column up the middle of the page here is really intended to indicate the status quo. So currently samples, the preparation, receipts, and management of those samples is handled by the lab. So, and it's typically a fairly manual process. Rock arrives at the lab, it's crushed, put into jars. Those jars then get run through a PhotonAssay unit. And the data that we produce goes back to the labs who do quality control, reporting, and pass it on to the end user customers, the miners. And predominantly we're doing that for gold, silver, and copper. So if we think about what does expanding up or downstream mean, so expanding upstream, I'll talk a little bit about the work that we're doing in automated sample preparation. And this is really thinking about what are the on-site labor requirements. So the fact PhotonAssay has substantially reduced the number of people you need to do analysis, prep then becomes the next bottleneck. So how can we make it easier for labs, particularly in remote locations, to quickly prepare samples to run through PhotonAssay? And then there are some interesting integration opportunities. We measure in real time. You could feed that information back to actually control and manage the preparation process. Moving downstream, so this is really thinking about what do we know about our samples beyond just the grade. So if we have metadata about those samples, where they came from, the types of materials, maybe how far down the borehole, the drill hole they were taken, how can we use that information to give more than just grade results to customers? How can we provide information that might provide them with geological insight or mineralogical insight that would help them run their operations more effectively? And then thinking about new elements, the other branch of expanding the footprint, really two directions that can go in. I mean, one, straightforwardly generating additional revenue from existing units. A good example there was when we added silver. Silver and gold can be assayed simultaneously, so they don't affect unit throughput, but we can charge a premium for providing that silver result. So what opportunities are there to provide additional elements in parallel, or to take up any unused capacity on existing units by running additional assay services? And look, another important point is thinking beyond just the revenue model is this idea of overcoming resistance. So one of the bits of feedback we sometimes get when proposing a new installation, the customer might want gold, but they might want 2 or 3 other important elements at the same time. And if we can't provide those, they have to maintain traditional lab infrastructure just to get those secondary elements. And sometimes that can be an obstacle to a customer making the complete switch over. So thinking about, a good example here would be deleterious or penalty elements. If a gold producer needs arsenic or sulfur or any of these other elements that currently we don't do, how can we afford the opportunity to measure those? So moving back a little bit to sort of the here and now. So the sort of structure of the talk, the first part will be very much about the engineering side of what we do and thinking about where our products are going. The second part of the talk will be looking at some of those future science opportunities. So as I think Dirk mentioned on the way through, we currently have 41 units deployed, referring to those as our Generation 1 product. Generation 2 is really thinking about where do we go to next. And we're looking at the 2 parallel supply chains here. So the XN units that Rob has mentioned will be developed. We'll continue our partnership with NucTech based up in Beijing. In parallel, we're looking at developing what we call the XC unit. And the theme there is really about getting away from a dependence on Chinese supply chains. Targeted at the North American market. So they would be a US-made accelerator, US-made detector, Australian-sourced automation, shielding, electrical components. So it's really about getting that 2 parallel routes for being able to maintain supply going forward. Done a lot of work on the automation system. We'll talk about that in the slide to come. Switching away from more linear-driven systems to an automatic robotic system gives us a lot of flexibility for future expansion. And we'll talk about some of the use improvements that we're working on. So the first of those 2, the Aussie contender, as we like to nickname it, the XC unit. This is the one that's all about decoupling from Chinese supply chains. So we've undertaken a big redesign of the automation in partnership with Sage, who are based literally 100 meters away, very convenient, and a Melbourne-based company called Automation Innovation. Bringing in the robot gives us a lot of performance benefits. We can run more samples, higher reliability. But the thing I'm excited about is it gives us a lot of flexibility because it's software controlled. If we in the future want to add additional assay steps or additional assay equipment inside the units, it becomes a software upgrade to access those services. on our existing units. There's no straightforward way to implement some of those changes. The X-ray source, which is a substantial physical component, but also a substantial cost component of the system. This is an electron linear accelerator. We've been working with a US-based company, Californian company called Accelerad. It's not something you can just go and buy off the shelf. They are quite customized, quite specialized bits of equipment. Accelerad work largely in the sterilization, irradiation space. So we've been working with them to modify their equipment to be suitable for PhotonAssay. And some nice benefits there. I mean, they're a small company. Their model is very much train the customer to support, maintain, and deploy the equipment. NucTech's model is more around maintaining ownership of that IP inside NucTech. So we think this is going to give us a lot of benefits in terms of being able to move more into the space of supporting the accelerators ourselves. Shielding and other core components, decoupling from Chinese manufacturers. The shielding is, it's a big 30-ton lead and steel structure. We've figured along the way we've kind of reaching the limits of Australian manufacturing capabilities. Sadly, the days when we used to build ships and things like that maybe are not behind us, but not quite as accessible as they used to be. So it's been an interesting journey just working with multiple partners to figure out how to actually do this kind of heavy engineering effectively and cost effectively in Australia. So where we're at the moment, well, we finished factory testing of XN. Sorry, take a step back. I'm jumping on to the next slide. We've finished the kind of assembly of the XC unit around about this middle of this year. We're currently in the thick of integration and testing. I think for those physically here, we'll be having a tour after the conclusion of this presentation. So you're welcome to come and see where we're at. It's definitely like a car with the bonnet up. The guts are on display, but the guys will be happy to walk you through some of the things that are going on there. With a view that rolling into next year, we'll get into the testing of that unit, start towards the beta design, and then the betas are the first products that we'll actually see roll out. So the other Gen-2 unit, the XN, the NucTech partnership unit. So we've aimed for as much commonality between the systems as possible. So they share automation design. A lot of the electrical and electronic changes will be shared between the two systems. Focus on significantly reducing the footprint of the unit, so smaller cabins, less height required. This might seem like a small point, but actually one of the obstacles to deployment of units has proven to be the availability of a suitable facility. We need a certain footprint, we need a certain height so that we can install and the units and get inside them for maintenance. Bringing the size of the unit down, we expect will make it much easier to kind of install into traditional or readily available on-site buildings and just smooth and simplify that deployment process. We've made quite a few changes to the shielding. I mean, we've got this sort of 30 plus tons of lead and plastic on the current design that has to be dismantled for shipping, reassembled on site. The new design splits it into two parts so that we can pretty much directly install on site. It's quicker, it's safer, less requirements for heavy machinery. Completed factory testing in the middle of this year, at the end of June. We gave our Chinese colleagues stick for being 3 days late on an 18-month project. When one thing you learn about China is when they give you a deadline, they stick to the deadline. We're currently have shipped and we're currently installing that unit in Perth and we'll start operations hopefully before the end of this year or early next year. It's the first time we've installed one, so we're learning a bunch of things as we go along. But installation seems to be going well. And just to drill down into one more sort of engineering component, and this is maybe a little bit nerdy, but don't worry, things will get nerdier when we get into the second half of the talk. One of the things that's sort of a detail that's important is when the jars go into our system, we need to know how full the jars are, and we need to know how much the material inside the jars blocks the gold signal that gets emitted when we activate the samples. And if we don't know either of those numbers accurately, it impacts on our ability to do the analysis. Not traditionally, historically, or to this point, we've determined both of those parameters are kind of determined in a slightly indirect way. So we use a camera system to measure the fill level that the operator has to control. The gamma ray transmission is measured internally as part of the analysis. And we're finding that whilst both of those things work okay, they're becoming the dominant source of uncertainty in the measurements that we perform, particularly for higher grade samples. So, we're always thinking about how to improve the quality of the analysis. So we've instituted a project to kind of redesign the way that the whole of this system works. So we're now effectively performing an X-ray of the jar to see where the material is. We're using a little radioisotope source to measure directly how much the radiation gets blocked inside the sample. Both of those methods work 3 or 4 times more accurately than our previous methods, significantly improve the analysis performance, and more importantly, they make the system easier to use. You're not reliant on an operator performing steps carefully. Anything that you can take away from the operator that makes the system more reliable, we see as being a good thing. And this has been designed, it'll go into the XC and the XN units by default, and it's been designed so that it can be rolled back into our existing Max 1 base as well. Okay, so to come to the second half, we'll talk a little bit about where are we going to broaden the offering. And this is moving beyond gold, silver, and copper in the analysis space. And so there's sort of four pillars here. So the first of those is doing more with standard PhotonAssay. So how can we take an existing unit and through changing the operating conditions or changing the software, extend the range of elements that we can measure? I'll talk a little bit about how we can make modifications to PhotonAssay that would enable us to get at certain elements using neutron analysis that we can't do with X-ray analysis. I'll talk briefly about some new assay technologies that we're looking at, so nothing to do with PhotonAssay, but capable of being integrated with our existing units, and a focus there on X-ray fluorescence. And then I'll conclude just talking a little bit about automated sample preparation. So new elements with standard PhotonAssay. I mean, we always, when we designed the unit, when we built the unit, it was done with the intention that by changing the operating parameters of the X-ray source, by changing the signals that we're looking at from the detectors, we can measure a wider range of elements. There are some certain basic physics requirements for an element to be accessible, but about half the elements in the periodic table meet those requirements. 2 elements that we're focusing on at the moment. The first of those is antimony, recognized as one of the critical minerals around the world. I think recently China's moving to kind of restrict supply of antimony, so there's a lot of interest in mines, Australia, North America, around the world in being able to increase antimony production. And so the analysis of that element is important. Commonly co-occurs with gold, so there's a nice synergy there between people who might be interested in measuring gold with PhotonAssay being able to add antimony as a secondary element. And then the other element that we're looking at is uranium. Again, commonly co-occurs with gold, particularly in some parts of Africa. Naturally radioactive, so the fact that we're pushing samples through extremely sensitive radiation detectors, there's a nice synergy there. And by activating the samples, we can also push to lower detection limits. So, testing work on both of those elements underway, hoping that next year we'll be starting to find some early commercial applications for those. I was warned about including too much physics, but sorry, physics is like fiber. A bit of physics in your diet is good for you. So there's going to be a minimal amount on this slide. And if you get enough of it, it's kind of like broccoli. You come to enjoy it after a while. So we've been thinking about how we can, PhotonAssay uses X-rays to activate materials. We've always had this sort of quirk that a byproduct of our X-ray sources, it also makes neutrons. And to date, we've treated them as like a bit of a pain. I mean, they're a source of radiation, so you have to shield them, you have to protect people from them. They can cause unwanted activation in the sample, which can affect your detection limit. So we put a lot of work in the original design of PhotonAssay to kind of suppressing the neutrons. But the thing about them is, I mean, they're a neutral particle, they come out of the atom, they're uncharged, that means they penetrate inside material, they get soaked up by certain elements, and that makes those elements activated. And so it's another pathway for actually being able to measure elements. And it tends to be complementary. Elements that you can't measure with X-rays, you can do with neutrons, and vice versa. So we've been thinking a little bit about this, and we've been carrying out some initial computer modeling of how we can tweak the heart of a PhotonAssay unit, the X-ray activation part of the system, in a way that lets us kind of switch on and off the neutron production. So we could have the neutron switched off, we do traditional gold analysis, we switch the neutrons on, and potentially it opens up quite a suite of elements that we wouldn't be able to get at any other way. Um, and a lot of interesting kind of commercial applications. We've been looking at critical minerals, scandium, vanadium, manganese, antimony, deleterious elements. In principle, we can do a lot of the rock-forming elements, silicon, aluminum, the bulk elements that make up your matrix, geologically interesting, and a range of commodity elements, aluminum, titanium, tin, and the rare earths, amongst others. So I should stress, early days, I've got my background's in computer modeling. I could talk computer modeling for hours, and I promise I won't. Experimental testing is something that we're just kicking off. But if over the next year or two, this pans out, then it gives us the opportunity to add quite a suite of new capabilities to PhotonAssay and to grow the accessible market. Conscious of time, I will try and wrap up in the next minute or two. So new technology. So these are things that are nothing to do with traditional photon assay. So we've been doing a lot of work this year on X-ray fluorescence. Now, this is a very widely used technique. I mean, it's certainly been around for decades, heavily used in the minerals industry. But we figure there's a bit of a niche here. So it's very quick and easy. I mean, anybody who's ever seen or used one of the little handheld XRF guns, you zap a rock and it gives you a reading. But those are not terribly accurate. The XRF really cares about matrix, mineralogy, and particle size effects. And if you've got a rough, rocky, unprepared sample, it's not going to give you a very high quality result. Labs, when they use XRF, go through extensive sample prep. So typically they fuse, they melt the sample into a glass, and you need to go down that extensive route if you're really going to get good quality quantitative data. We're sort of thinking, is there a path to steer through the middle here? So quite a few of our team come from a background with developing X-ray fluorescence for on-stream analysis, so measuring process materials where we have no sample prep done. And we think there are some opportunities to kind of use some of those ideas, but also a synergy between PhotonAssay and XRF. So there's a bunch of elements that PhotonAssay measures, not in themselves interesting for commercial reasons, but we could tie that PhotonAssay measurement, which is very accurate, against a semi-quantitative XRF analysis in a way that might give us the best of both technologies. We could get quantitative data out of XRF in a way that other people historically haven't been able to do. Again, very early R&D stages. We've fortunately gone beyond the modeling. From the photo, we've got a test rig running at the moment. Interesting early results on looking at deleterious elements in copper samples. Watch this space. Nice thing about XRF, it's a very small, compact package, easy to integrate into an existing PhotonAssay unit. You can run it in parallel, so you wouldn't affect throughput. Very nice kind of potential, technical and market benefits if we can make it work. And then the last slide I think I'm really going to talk to is a little bit about automated sample preparation. And this is interestingly one that the Chrysos kind of hasn't been driving itself, or not until recently. So there's a bunch of sort of large providers out there that build automated sample handling and lab automation equipment. And a few of these have kind of started to advertise PhotonAssay targeted preparation equipment, sort of independently, which is kind of cool. It's like PhotonAssay is becoming a thing. It's becoming something that people can actually target. So this is all about replacing the very manual work of receiving bags of samples, crushing, splitting, prepping, putting the material into jars. If you ever visit a mineral assay lab, a big part of the footprint is just people doing this very routine, very repetitive work. So ideas around automating this are speed, consistency, reliability, but also just managing your labor requirements. So I pulled some numbers. So a typical traditional 1,500 sample a day fire assay lab might have something like 20, 25 people, working the shifts in the lab. A big chunk of that is in the assay space. PhotonAssay already reduces that down to basically one person per shift. Your next big hit is people involved in sample prep, and potentially that could be halved as well. So suddenly you're looking at operating a lab on 10 or 12 people instead of 25 people. And if that lab is in the Sahel or the Canadian Arctic or, even the Australian outback, costs of people getting them there, fly in, fly out, accommodating them are huge. So real kind of benefits from both a safety, a health, a reliability, and a commercial perspective. And I think that's it. I just wanted to close on one thought, which is really, and this might sound self-serving as a scientist, but for me, the long-term strength of any technology business is not in the IP that you own. It's about the speed and your ability to generate IP. It's your ability to respond to new threats, to new opportunities, to new problems as they arise. As a physicist, I would say it's about momentum, the power with which you're going forward rather than the position that you're at the moment. But for me, that underpins what the R&D team in Chrysos is about. We spent 25 years building the basic IP behind PhotonAssay back when I was a CSRO and in the early days of Chrysos. It's now what's our momentum going forward from here. So thank you very much for your attention.